Okay, welcome back everyone. Welcome to the fourth lecture. Today we're going to discuss about inference. So this is a particular topic in Econometrics 1, which is quite important for the progression of your knowledge. So in particular, in the past sessions, we've talked about estimation, particularly estimation of the the parameters, the betas, as well as the standard errors for the betas. Now, using the estimated coefficients as well as the standard errors, we're now going to do some inference. So this is going to be the core discussion for the lecture this afternoon. Again, if you have any questions or if you have any clarification point, please unmute yourself and then throw out the questions. I will also, from time to time, provide you with the opportunity to ask questions. Yes, any point? Okay, let's start. Let's discuss about statistical inference. Again, you should be able to kind of like recall topics regarding statistical inference, both from your Statistics 1 as well as Statistics 2 course. I guess you have some comprehensive discussions on statistical inference. And so I'm really hoping that today's lecture is just going to be a confirmation on what you've learned and hopefully kind of like a refresher on the stuff that you've learned in the previous statistics courses. In this lecture, I will also provide you with an illustration on how to do statistical inference using Stata. Okay, hopefully the illustration will provide you with a kind of like a detail on how to do statistical inference, and then to also understand methods to do statistical inference. And so let's start. Again, in the previous meeting, we used OLS to obtain unbiased estimates of the parameters in the model. So we always talked about population and then population regression function, and then one of the key issues is that these parameters are not observed in the population because it's costly to get population data, and then it's going to be taking us a lot of time to get the population data, and so it's more sensible for us to get a sample that is representative to the population. In other words, it's always good to get an unbiased sample or a representative sample for the population that we're interested in. And so given the sample, then we'd like to use the OLS to estimate the parameters, okay? And so given the sample, we estimate not only the beta case, okay, but also the standard error of the beta head case. You can also recall the assumptions that we need to obtain an unbiased estimate of betas, as well as an unbiased estimate of the standard errors. So if you recall, there are 4 assumptions so that we get an unbiased estimate of the parameters beta. We also need 5 assumptions to get an unbiased estimate of the standard errors. Anyone would like to state the 4 assumptions such that we get an unbiased estimate of the betas? Anyone recall the assumptions? If you don't remember all, perhaps you can state what's the key assumptions to obtain an unbiased estimate of the betas. Anyone? Okay. All right. Let me. All right, Ahmad Zaki, do you recall one key assumptions to get an unbiased estimate of the beta? Okay, perhaps Arzak Zidan. Again, what's the key assumption on to get an unbiased estimate of the beta?
Hello, sir. Do you hear me?
Yes, go ahead.
Probably that the U is unrelated with the B1 and B2.
Okay, so assuming that we're interested in estimating beta 1 and beta 2, then we want that the unobserved variables are uncorrelated with the beta 1 and beta 2. Okay, so that's the
Yes,
assumption. Okay, all right, good. Okay, so one additional, okay, just going back, there are 4 assumptions that we need to get an unbiased estimates of the betas. They are linear in parameters, and then we have a representative sample. Basically, it's a random sample of the population. Number 3, we have no perfect collinearity, and we also have variations in the explanatory variable x. And then the 4th assumption is the 0 conditional mean assumption. Again, this is the assumptions that we've gone through over and over again. So hopefully it stick, in your kind of like in your head that this is kind of like the key assumption. All right, one additional assumption that we need to obtain an unbiased estimate of the standard error. Anyone recall? What's the one additional assumption?
Sir?
Go ahead. Yes.
Is it homoscedasticity?
Yes. So it's the homoscedasticity. So basically, if you have assumptions 1, 2, 3, 4, and 5, then you'll be able to get an unbiased estimate of the standard error. So basically, those are the key assumptions that we need. And today we're going to discuss an additional assumption to get into the inference part of the econometrics. Okay. All right. So going back to the discussion again, we want to obtain an unbiased estimate of the return to education. Anyone wants to state what's the parameter that depicts the return to education in this model?
Sir?
Yes, go ahead.
Is it the beta behind the beta?
Yeah. So the beta associated with the education variable is going to be the parameter that depicts or illustrates the returns to education. Okay. So we're really interested in estimating the beta. Again, we don't know what's the value of beta because it's a parameter in the population. And so we're trying to use a random sample to estimate the beta. Okay. So that's the idea. Now, what we like to do is that given the data, can we conclude that the return to education is non-zero? Okay. So for example, suppose that I use the data, and then from the data, I estimate that the estimated parameter or the estimated coefficient is 0.039. Okay. Since we have a log wage in the left-hand side and then education in the right-hand side, always remember that in order for us to interpret, we need to multiply it by 100%. Okay. And so the estimated return to education is about 3.9%. So additional year of schooling is associated with higher wages by 3.9%. Now the question is whether the 0.039 is actually different to 0. Okay. In other words, we want to know whether 0.039 is statistically significant. So that's kind of like the goal of the discussion today. We want to know whether or not the estimated coefficient is actually different to 0. Okay. So we're going to do hypothesis tests about the population parameters. Okay. For example, we're interested in doing a hypothesis test on the return to education. We would also like to construct confidence intervals. Okay. So confidence intervals is another feature of the estimation that's going to be quite useful, not only to identify whether there is a significant effect of a particular variable, but confidence intervals will also allow you to provide you with some, view of how the estimated coefficient vary, cross estimation. So that's also an important part of inference as well. Okay, so the materials for this discussion is going to be chapter 4 of Jeffrey Wooldridge Introductory Econometrics. And then if you're interested in looking back at the statistical foundations that you need to do hypothesis tests, then you can also visit Appendix C1, C2, and then C5 and 6 in Jeffrey Wooldridge textbook. Okay, again, materials in these appendices are already being taught in the Statistics 2 course or the Statistics 1 course. So hopefully this is not, these materials are not going to be that difficult for you. All right. So before we start, I want to get to the idea of sampling distributions of the OLS estimators. Okay. And so again, the OLS estimators are going to be random variables, okay, whose distribution is a function of the sample size and the model specification. And so if you have a population of interest, and then from that population of interest, you get a random sample, okay? So from that random sample, you get an estimate of beta, okay? Now suppose that, so this is just, a supposition. Suppose that you have the luxury to get another random sample from the population. Will you get the same beta head, or will you get a different beta head from the estimation? Anyone? So suppose you have the luxury to get another random sample from the population. Will you get the same beta head, or will you get a different beta head?
Different, sir.
Yeah, very good. So as Alexander said, we're going to get a different beta. So for different random sample, we're going to get a different beta head. Okay. Now also with different sample size, we may get a different distribution on how these random variables, are distributed across estimations. So for example, the larger the size of the sample that you have, would you get like a wider distribution, or will you get a tighter distribution? Which one is true if you have more sample size?
Tighter, sir.
Come again?
Tighter.
Yes, very good. So if you have like a larger sample size, then your sampling distribution, theoretically, again, is going to be tighter. Okay, so again, this is the idea of sampling distributions when you guys learn in statistics too. So please take time to recall the meaning of sampling distributions. Okay. Now, we already know their expected values and their variances. However, for the hypothesis test, we need to know their distribution. Okay. And so we now know beta heads. Okay. We also know the standard error of beta head. Those are the two statistics that we can estimate from the sample. Now we need additional information, and that additional information is the distributions of the beta head. Okay, actually the distribution of the beta. Now, in order for us to get the distributions, we need an assumption. So this is the additional assumption that I talked about in the beginning of the lecture, which is the assumption of normal distribution. Okay, and this is going to be the sixth assumption for the multiple linear regression. So we have linear parameters, and then we have random sample. We have no perfect collinearity or no multicollinearity. We also have variation in X, and then the zero conditional mean assumption, the homoscedasticity assumption, and then the sixth assumption, which is the normal distribution of the unobserved factors or the errors. Okay, so that's going to be one of the additional assumptions that we need. So just to kind of like state the definition or state the assumption. So the sixth assumption, normality of the error terms or the normality of the unobserved variable. So the error term u is independent of the covariates x1, x2, x3, x4 until xk, and is normally distributed with zero mean and variance sigma square. Okay, so again, this is key, that the error term is normally distributed with zero mean and variance sigma square. So this is going to be the assumption. Again, this is the assumption, right? So, suppose that we know the population, okay? It may be true that in population, it's not normally distributed, okay? And so this is the assumption that we need for us to do the inference later on, okay? And so again, this is going to be quite key, that the form of the variance and the distribution is not going to depend on any explanatory variables. In this particular case, we're going to also assume homoscedasticity, which we already assumed in the fifth OLS assumption. Okay, so this implies that the distribution of y conditional on x is going to be normally distributed around the regression line. Okay, just to repeat, the distribution on y conditional on the observable variable x is going to be normally distributed around the regression line. Okay, so basically you're going to have, so this is just an illustration, which I think we'll see in the next slide. So suppose this is x, this is y, and this is the regression line. Then the factors that we do not observe is going to be normally distributed around the regression line. That's going to be kind of like the implication of this assumption. Okay, and remember, the distribution of the prediction y around the regression line is going to be constant since we have the homoscedasticity assumption. Okay, this is the illustration that I gave you just a moment ago. Basically, the unobserved variable is going to be normally distributed around the regression line. Okay, so this is based on the fifth assumption of homoscedasticity. It's also based on the sixth assumption that the error terms is normally distributed around the regression line. All right, any questions, clarifications so far from this point? So this is quite conceptual. I understand that the discussion is quite abstract, but hopefully it's going to provide you with a foundation, particularly statistical foundation, for you to proceed to the subsequent discussions. So feel free to ask anything that you think needs clarifying. Okay, very good. So again, from time to time, if you have any questions or you'd like me to clarify some of the points, feel free to unmute and then ask the questions. Again, I don't want anyone to get stuck in a particular concept without knowing it, since we're going to use it in the subsequent discussions. Okay, very good. So again, what's the discussion so far? The discussion so far is that we estimate betas from the data, from the sample. We also estimate the standard error. Now, in order for us to make an inference about the beta using the sample, then we need an assumption on the distribution. So in particular, we're going to assume that the unobservable is normally distributed. And so given that the unobservable is normally distributed, then the variable, the y variable is going to be normally distributed around the regression line. Okay, so that's going to be the idea. All right. And so at the end of the day, we'd like to make some assumptions on the, on the normality so that we can do hypothesis testing. Okay, so in order for us to do a hypothesis testing, then what we want to do is that we want to know what's the distribution of the parameters themselves. Okay. So again, what's going to be, the goal? We have betas. Okay. We also have the standard error of this betas. Okay. Now, given the assumptions from 1, 2, 3, 4, 5, and 6, then we can say that the distribution of the beta hat is going to follow a normal distribution with a mean beta, this is the mean, and the variance beta hat j. Okay. So again, under the normality assumption, then the estimated parameter beta is normally distributed around beta with variance beta j. Now the question is, do we know the variance of beta hat j? Or given the sample, can we estimate the variance of beta hat j? Okay. In other words, can we actually estimate the standard deviation of beta hat j? If you remember, just look at this formula. Can you get sigma square? Can you get SSDJ? Can you get 1 minus R squared J from the data? Anyone recall? Can we get those data from the sample? Or can we estimate that from the sample? Anyone remember? Okay. So basically, we don't know the value of sigma square, right? So if you guys remember, what is sigma square? Sigma square is going to be the variance of u conditional on x. Okay, so this is basically the variance of the unobservable conditional on x in the population. Do we know the value of the parameter in the population? In general, no. And so we need an estimate of the sigma square to get an estimate of the standard deviation. Okay, so that's going to be the discussion in the next slide. Okay, now before I go there, a lot of times we also do standardization. Okay, and so let me go out and then use a separate note. Suppose that you have a random variable, okay, and the random variable follows a normal distribution with mean mu and then variance sigma square. Okay. Now, if we do a standardization, so we subtract the random variable with the mean, and then we divide this with the standard deviation, then it's going to follow a normal distribution with a mean of 0 and a variance of 1. Okay, so remember, this is the standardization process that you learned not only in statistics 2, but also back in your statistics 1 course. Okay, so this is something that you should be familiar with. Okay, so the idea is that the random sample is distributed normally around the mean and the variance. Now, similarly, our estimate beta hat j is normally distributed around the true mean beta j and then the variance of beta hat j. Okay, and so if we do just a standardization process, then beta hat j minus beta j divided by the standard deviation of beta hat j is going to follow a normal distribution with mean of 0 and variance of 1. Okay, so this is kind of like the statistical foundation that we need to do a hypothesis test. However, okay, so this is kind of like a additional remark from this. However, again, we don't know what's the value of the standard deviation. Why can't we know the value of the standard deviation? We don't know what's the value of the standard deviation because remember, we don't know the value of sigma square, which is the variance of the unobservable conditional on x. Why don't we know the value? Well, it's because in general, it's the population parameter, and a lot of times you don't know the population parameter. Okay, and so if you recall from your statistics 2 course, if you don't have variance, what can you do? Well, if you don't have the population variance, then what you can do is to use the sample variance. Okay, so instead of using the sigma square, we can now use the sample variance. Okay, this is the sample variance. Again, so if you follow closely our lecture from lecture 2 and 3 in particular, we always go back and forth. We have the population regression function, we have the parameters in the population, and given the data, we're going to estimate those parameters. Okay, so we go back and forth a lot of times. Okay, so if we now use the sample variation, then the distribution is going to be quite different. Okay, and so the distribution now is not a normal distribution, but it's going to follow a student t distribution. Okay, so in particular, if we assume that beta hat j is normally distributed, okay, with the mean of beta j and the variance of beta hat j, then beta hat j minus the true value in the parameter. Do we know the true value in the parameter? We don't know, but let's discuss that in a few moments. And then divided by the standard error of the beta hat j. Now, this is going to follow a student t distribution with a particular degree of freedom. What's the degree of freedom? The degree of freedom is the number of observation n minus the number of parameter and number of variable, okay, and then minus 1. Okay, we'll talk about this later on. Okay, now as the degree of freedom increases, okay, and so if the number of observation relative to the number of variable is large enough, then the student t distribution is actually very, very, very close to the standard normal distribution. Okay, so again, if the number of observation relative to the number of variable is very, very large, okay, it's actually going to be very close to the standard normal distribution. Okay, so let's go back to recap. Okay, given the 6th assumption, which is the normality of the error term, then we can assume that the estimated beta is normally distributed around the true value of beta, which is this part, and some variance. Okay. However, we don't know the value of variance in the population. And so if we don't know the value of the variance in the population, we're going to use sample variance. Okay. And since we now use the sample variance, we no longer use standard deviation. We now use the standard error. Okay. And the distribution, because we're using the standard error or the sample variance, is no longer the normal distribution, but it's going to be the student t distribution with some degree of freedom. In this particular case, the degree of freedom is the number of observation minus k, the number of variables minus 1. Okay. Again, if the number of observations relative to the number of variables is large enough, then we're going to have a t distribution that is very, very, very close to the normal distribution. Okay. Any questions? Okay, so if you think that some of the, if you think that some of the concepts are, quite abstract, or it's quite, foreign to you guys, just recall your statistics 1 and statistics 2 courses, and I'm pretty sure that they already discussed this cases. And so you'll be able to go through it and then probably do some recall. Okay, all right, good. If there is no other questions, I'm going to go to the next slide and talk about the idea behind hypothesis testing. Okay, so we already have, we already did a discussion on the distribution of the betas, and so given the distributions of the betas or the parameter in particular, we're going to discuss the idea behind hypothesis testing. Okay, all right. So actually, this is going to be kind of like one of the exciting part of doing econometrics. Okay, not only that, we want to estimate the betas and also the standard errors. We also want to know whether or not a particular variable is statistically significant. Okay, we want to know whether a particular variable actually has a relationship with the variable or the outcome variable of interest. Okay, so for example, do people with higher education or do people with higher education tends to have higher wages in the labor market? So that's the correlation that we're interested in. Or for example, do extra expenditures on children improve performance in the school? That's another line of questions that we're interested in. And so to be able to say something on whether or not a particular variable is really correlated or is supported by the data that is correlated or it has a particular effect on the outcome variable, we need to do hypothesis testing. And so what do we want to know from a hypothesis testing? So basically from hypothesis testing, we're going to be able to determine whether or not a specific parameter, now I'm not going to use beta, but for the illustration, I'm going to use theta. So we want to know whether the parameter theta can be statistically distinguished from some specific value. Okay, so in general, we want to know whether or not there is an effect or whether or not there is a correlation between two variables. Okay, and so like kind of like the status quo is that there is no relationship, there is no effect at all. And so if we state that there is no effect or there is no correlation, then we should say that theta is equal to 0. Okay, so for example, if I write a very simple population regression function, y is equal to beta 0 plus beta 1x plus u. Okay, so we want to know whether or not x has an effect on y. Okay, so this is what we're interested in. And so what we want to know is that whether or not beta 1 is actually different to 0. If beta 1 is different to 0, it could be positive, it could be negative. And so x has a correlation or has an effect on y. However, if beta 1 is equal to 0, then x has no effect on y. So this is not going to be like precisely like, the value should be 0, but to the value we, is the value that we see from the estimate is really close to 0, or is actually very far away from 0. So that's going to be the questions that we're going to ask in the hypothesis testing. Okay, so the formal setup is the following. You're going to state your null hypothesis. Okay, so your null hypothesis usually involves an equality. So in this particular case, the null hypothesis is that there is no effect. Okay, so no effect. Okay, and then the alternative hypothesis is that there is an effect. Okay, so theta is not equal to 0. So by saying that there is an effect, the effect could be positive, the effect could be negative, depending on the estimate, that we get from the data. Okay, so our approach is the following. We're going to assume that the null hypothesis is true, and then under the assumption that the null hypothesis is true, we can obtain a distribution for our estimator. Okay, so suppose that someone gets convicted, okay, for a felony, for example. We're going to assume that the individual is innocent unless the data or the evidence proves otherwise. Okay, so that's the idea. And so we're going to determine if the estimated theta hat is very unlikely given this distribution. Okay, so again, we have the null hypothesis. And so given the null hypothesis, we want to know whether or not the estimated parameter is unlikely or not given this distribution. If it's unlikely, what do? We reject the null hypothesis. Okay. If theta hat is actually likely given the null hypothesis, and so the null hypothesis is not rejected. Okay. And so I just want you guys to follow the convention. So it's not about accepting versus rejecting. It's actually whether or not the null hypothesis is rejected versus null hypothesis is not rejected. Okay, so please, pretty please, do not use accepted versus rejected, but instead use rejected versus not rejected. Okay, what's the idea behind just this simple wording? The idea is that sometimes we cannot and we do not reject the null hypothesis because we do not have enough evidence. Okay, perhaps with some evidence we can reject the null hypothesis. Okay, so again, we do not accept the null hypothesis, but it's just that we cannot reject the null hypothesis. Right? It might be quite subtle, but it has a different meaning, and then it has a different implication as well. Okay, so again, just to give you guys a particular illustration, so suppose that this is the distribution under the null hypothesis again. Okay, so again, this is the distribution under the null hypothesis, say beta j equals to 0. Okay, now this is what we assume. Okay, now suppose that we get a sample, we get a data, and then from the data we're going to do some estimation, and then from the estimation we found out that the value of the estimate is right here. Okay, so the beta hat j is right there. Now we want to know whether or not this beta hat j is very unlikely. Okay, so if this beta hat j is very unlikely, then we're going to say that we reject the beta j, we reject the null hypothesis. Okay, another example. Suppose that our estimate, or maybe I'm going to use the other side right here. Suppose that our estimate is right here. Okay, so it means that the beta hat j is actually very likely given the assumed distribution. And so in this particular case, we're going to state that the null hypothesis is not rejected. Okay, and so again, given the assumed distribution under the null hypothesis, we want to know whether or not the beta hat j is unlikely, in which case we're going to reject the null hypothesis, or it's actually very likely that we do not reject the null hypothesis. Okay, so that's the idea behind the hypothesis testing. Okay, again, we're going to have like variation in the hypothesis testing. We can have a one-sided test. We can have the right tail test. We can have the left tail test. We can have the two-sided test. Later on we will also discuss about the F test. And so we're going to face some various alternatives of hypothesis testing depending on what we're testing, but the idea is the same. So given the assumed distribution under the null hypothesis, whether or not the estimated coefficient is likely or it's actually very unlikely. If it's likely, then we're not going to reject the null hypothesis. But if it's very unlikely, say it's on the far right of the distribution or on the far left of the distribution, then we're going to reject the null hypothesis. Okay, so that's the idea. Okay, just going back to the slide, and then I'm gonna just provide you with a follow-up discussion. The most common hypothesis test is the t-test for a single slope coefficient beta hat j. Okay, so we're interested in whether or not we get a non-zero return to education. Okay, and so in that particular case, the null hypothesis and the alternative hypothesis are the following. Okay, and so the t-test tells us if we can determine statistically that it's unlikely beta j equals to 0. Okay, if it is unlikely, then we're going to say that we reject the null hypothesis. Just a particular note, again, this is something that is quite fundamental, but a lot of students actually miss this. When you state your null and alternative hypothesis, remember it's about the parameter, okay? So it's a hypothesis about the parameter, in this case is beta j. However, in the past years, some students write the null and alternative hypothesis for the statistics, okay, which is quite false. Why? Because again, we want to know whether or not the true value in the parameter is equal to 0. Is actually not equal to 0. It's not about the statistics. The statistic is something that we're going to use in the hypothesis testing itself, but it's not for us to make an alternative or the null hypothesis from. So it's a very fundamental and conceptual notes. I don't want you guys to make the same errors as a lot of the students did in the past. Okay, any questions on the idea behind the null hypothesis and then hypothesis testing before we get into the test statistics? Okay, so basically the test statistics is going to be the statistics that going to determine whether or not we reject the null hypothesis or we do not reject the null hypothesis. Okay. Questions, clarification? Okay, very good. So I'll continue and discuss the t statistics, or some people said it's the t ratio. Okay, so first of all, before we do any calculation of the t statistics and the t ratio, we always have to revisit what's the null hypothesis. Okay, now in this particular case, we're going to assume that the null hypothesis is that the beta j equals to 0. Okay, now in other cases, perhaps we're interested in the null hypothesis of beta j equals to 1, or in other cases we're interested in the null hypothesis beta j equals to some constant a. Okay, again, it really depends on the research questions in hand, but in general what we're interested in is to look at whether or not there is an effect or not. Okay, if there is no effect, then beta j is just equal to 0. So that's what we're going to test. Okay, and the t statistics or the t ratio is actually very straightforward. It's just the difference between the estimated coefficient. Where do we get this? We get this from the data and use OLS. Okay, and then we're going to subtract that with the value of the beta in the population, and again we're going to assume that it's 0. Okay, and so it's basically just beta hat j. Okay, and then divided by the standard error of beta hat j. Okay? And so basically the t statistic is just beta hat j divided by the standard error of beta hat j, and it's going to follow a student t distribution with a degrees of freedom of n minus k minus 1. Okay, and so the t statistic will be used to test the null hypothesis. Okay, so remember, it could be that okay, so I guess I'll make a better normal distribution, which is very hard to make, but let's assume that's a normal distribution. Okay, suppose that we get something here. Okay, then we can say that, oh, perhaps it's very unlikely that the value is actually 0, or perhaps we get the value right here. given the null distribution, in that case, it's actually very likely. And so we want to make a statement like how far away is our estimate from 0, okay? And how do we make that conclusion, or how do we make that statement? Well, we're going to use the t-statistic, okay? And then given the t-statistic, we're going to decide whether or not it's far away, in which case we reject the null hypothesis, or it's actually very, very close, so that we do not reject the null hypothesis. Okay. So we now have these statistics. What else do we need so that we can say that it's far away or it's actually not that far away? What we need is a rejection rule. Okay. So we need a rejection rule such that if it's true, then the null hypothesis is rejected with a small probability. Okay. And that probability is usually referred to as alpha. Okay. In this case, alpha is equals to 0.05 or 5%. Okay. In social science, we use usually 5% significance level. Some people also use usually 1% significance level, and some people use the 10% significance level. Okay. So the idea is that alpha should be quite low. Okay, if you can get lower than 1%, that's actually better. Why? If you recall your statistics discussion, alpha is the probability of type 1 error. Okay, so it's basically the probability that we reject the true null hypothesis. Okay, again, it's the probability that we reject the true null hypothesis. Well, if the null hypothesis is true, then we shouldn't reject it. But again, there is some probability that given the data, we can reject the null hypothesis that is true. Now, that is something that we want to avoid, okay? Making what's called the type 1 error. So if we say that something is actually, suppose that the two variables are not correlated, or X doesn't have an effect on Y, that's the true kind of like the true relationship. However, given the data, you actually say, hey, there is an effect of X on Y. We want that kind of, occurrence happens with a very, very small probability. And so in general, in economics, in general and in economics, we want to use very low alpha, okay? The alpha that is usually used in practice is 1%, 5%, and then 10%, okay? So alpha of 1% means that there is a 1% probability that we reject the true null hypothesis, okay? Okay, any questions before we go? Again, a lot of the slides that we've discussed so far is actually kind of like a refresher to your statistics course, but hopefully I've given enough so that you can recall the foundation and be able to follow the rest of the discussion. Okay, go ahead.
Sir, may I ask a question?
Sure, go ahead.
Before you said about unlikely, further away from the beta, from the middle point of the normal distribution. But what does unlikely and likely means in the normal distribution?
Right. Okay. So again, when we talked about, okay, so suppose that, So suppose that this is the distribution, right? And then this is the true value, and suppose that we assume that the true value is 0. Okay. Now, the distribution, or called the sampling distribution, is a distribution that happens if we do repeated sampling. Okay. So suppose that we do a sampling, and then we get an estimate. We get another sample, we get a different value estimate. We do that, say, 100 of times. And then with the different value of the estimates, we're going to make a distribution. And that distribution is called a sampling distribution. And so the distribution that you see here is called a sampling distribution. Okay. Now, suppose now, again, repeated sampling is in theory. Okay. You do not have in practice the luxury to do a repeated sampling. Usually you just have one sample that you randomly draw from the population. It's usually a very expensive sample since you draw it randomly from the population. Okay, so that's one. Now, given the distribution, how likely it is that given a sample, we're going to estimate, or we're going to get an estimate something right here. Okay. And so why do I use likely? Because again, it's all about probability. It's the random sample. It's the random variable. Okay. And so if it's here, then it's very, very, very unlikely, assuming the distribution under the null. Okay. However, in this particular point, it could be very likely if there is the true distribution. Okay. So I'm giving you another concept here, but this is just to give you an illustration that if it's unlikely that it's coming from the null hypothesis, then it could be coming from another distribution. So that's kind of like the idea of why I use likely or unlikely. Don't worry if it doesn't, stick to you at this moment. Hopefully, if you give it another try or two, then you'll be able to understand the meaning behind this. Okay, that's fine. Any other clarification? Okay.
Hello, sir.
Go ahead.
Earlier you mentioned about the usage of the term rejected and not rejected, but I still don't really get the point on why is the term accepted not used in the hypothesis testing.
Well, the simple idea is just because we don't know whether the true or like the null hypothesis is true. Okay. Again, going back to the discussion of this graph right here, we only assume that the null hypothesis is true. Do we know that it's actually true? No. Why? Again, we don't know what's the value in the population. But by saying that you accept, it means that you know that the null hypothesis is true. Okay. However, it might not be true. Maybe we don't have enough evidence. By saying that we don't have enough evidence, it means that we don't have, or enough sample size to actually reject the null hypothesis. So since we never know whether or not a null hypothesis is true or not, then we don't say that we accept, but rather we say we reject versus not reject. So we don't say which one is true because we never know what's true, right? But given the given statistics and then given the assumption on the distribution, then statistically we can say that it's different to zero. In that case, then the assumed null hypothesis is rejected. Okay. So that's
okay,
the idea. Yeah, go ahead.
Probably another question, sir, with regards to the rejection rule. Because earlier you mentioned that usually the use number is 5%, but who actually determines this rejection rule number? Is it depends on the researchers itself, or?
Yeah, exactly. So the idea is that we want alpha to be as small, as small as possible. So if we can get 1%, I think it would be nice. If you can get 0.1% or 0.01%, that's also nice as well. So the idea is that the smaller the alpha, the better. It's just kind of like a convention in social science. We usually use the 1% significance level, 5% significance level, and 10% significance level. And so basically, when we do reporting of regression results, not only that we want to report just one significant level, but we usually report the 1%, 5%, as well as the 10% significance level. So there's no one significance level for all, but usually we use the 3. Okay, it's different in other disciplines. So for example, in the medical faculty, where they use randomized controlled trials and they want to know whether or not a particular intervention is effective or not, then perhaps they want to use a very low alpha such that they're really sure that they do not reject the true null hypothesis. Okay, so that's the case. But in social science, where everything is quite complex, where everything, where there's a lot of unobservable variable, we usually use the 1, 5, and 10% significance level. Yeah. All right. Another before I continue to the testing again.
Yes, sir. I would like to ask a question.
Go ahead.
Okay, so from our main textbook, Wooldridge, part 4, 4.2a, I noticed one interesting passage. So it says that as the significance level falls, the critical value increases. I'm actually quite interested with the regression rule, where we usually use 5% degrees of freedom. If we use a higher significance, a lower significance level, then higher significant levels should automatically be rejected. So if we pick 1%, then 5% and 10% should be rejected, right? Then in journal articles, we usually see rejection results mentioning that one result is supported at let's say 0.01 significance level, or maybe at 0.05 significance level, and at 0.1 significance level. Then my question is, if we use lower significance level so that the higher significance level can be automatically rejected, then why don't we just go straight into using the lowest one, the lowest significance level?
Okay, thank you, Zaki. So yes, as you said, or and also as the textbook said, the lower the significance level, or the lower the assumed significance level, then the higher the critical value. It means that you really need to have strong evidence in order for us to reject the null hypothesis if the significance level is very, very low, right? Why? Because we want to have more confidence that we really reject the false null hypothesis, or we want to minimize the fact that we reject the true null hypothesis. So that's the idea. Now, as you said, if a particular variable is significant at, say, a 1% significance level, then it's also significant at the 5% as well as the 10% significance level. That's true. But why do we still want to report several significance levels, say 1, 5, and 10%? we still want to report those because not only that we test one particular variable, but sometimes we test several variables. Okay, so one variable could be significant at the 1% level, but another variable could be significant at the 5% significance level. So we don't know, and so having the 3 alternatives will provide us with different options. Another point that I'd like to make is that we don't always use the t-statistics and the critical value, but a lot of times we actually use the p-value. Okay, and knowing and estimating the p-value can actually be beneficial. It's going to provide you with, kind of like a faster way to identify whether or not you reject the null hypothesis or you fail to reject the null hypothesis. Okay, so that's the idea and something that we're going to discuss. Okay, all right, so I'm going to continue and then start the discussion on the actual testing. And so we're going to test against one-sided alternative. So for example, the theory says that there is a positive relationship between working experience and wages in the labor market. And so if the if the theory says that there is a positive relationship between the working years of working experience and then wages, then you can state in your alternative hypothesis that there is a positive relationship. Okay, or for example, if you're interested in a particular intervention, and say it's an iron pill intervention. So an iron pill intervention is an intervention given to mothers, particularly pregnant mothers. And so it's going to provide the nutrition that it needs during pregnancy. One of the goals of providing an iron pill intervention is that in the future, the kid, does not become stunted. Okay, and so if that's the case, we want to know whether or not the null hypothesis is beta j equals to 0, and then the alternative is that whether there is a positive effect. It means that if you receive the intervention, the incidence of stunting is actually lower. In that case, we're going to use a left tail or a left tail test. So the idea is that we reject the null hypothesis in favor of the alternative hypothesis if the estimated coefficient in this particular case is too large, okay, larger than a critical value. In this case, we reject the null hypothesis in favor of the alternative hypothesis if the estimated coefficient is too small, okay, smaller than a critical value. And so we've been saying about critical value. What's the value of the critical value? Well, if the null hypothesis is true, it is going to be rejected in, for example, 5% of the cases. So what we want to know next is to actually understand how we get the critical value. Well, the critical value is going to depend on the number of observations in the sample, or basically just the sample size. It's also going to depend on the number of variables used in the regression. So basically, it's going to depend on the degrees of freedom. Okay, and so we're going to use the t-table, the student t-table, to determine what's the critical value. Okay, now in this particular case, the point of the t-distribution with 28 degrees of freedom is 1.071. Okay, and so if the t-statistic or the t-ratio exceeds 1.701, then we reject the null hypothesis at the 5% significant level. Okay, if the t-statistic or the t-ratio is actually lower than 1.701, then we do not reject the null hypothesis. Okay, now how do we know the value of 1.701? Well, it's actually taken from the student t-table. Now, the first thing that you like to do is you first want to identify whether or not it's a one-sided or a two-sided alternative. Since we're making, the statement is the alternative is beta j is larger than 0, it means that we use a one-tailed test. And so we're going to refer to this particular column. Okay. Now suppose that, oops, okay, right, my fault. Suppose we're going to focus on the one-tailed test, so we're going to focus on this particular row. Okay. And since we assume that the significance level is 5% or 0.05, we're going to focus on this particular column. All right. What's the degrees of freedom? So the degrees of freedom is n minus k minus 1. And for 28 degrees of freedom, then the critical value is 1.701. Okay. That's how you determine the critical value. Now, whether or not you reject the null hypothesis or you do not reject the null hypothesis is going to depend on the t-statistics and the t-ratio. How do we get the t-statistics and the t-ratio? Well, it's just a ratio between the estimated coefficient beta hat j minus the assumed value of beta in the population, which in most cases is 0, divided by the standard error of beta hat j. That's the t-statistics. Compare that with the 1.701. Now, just be careful. Really depends on the sign of the alternative hypothesis. So suppose that your alternative hypothesis is actually beta j lower than 0. Okay, then your critical value is now minus 1.701. Why? Because you're testing here. This is the 5% level. And so it's 1.701. Okay, so be careful. It really depends on the alternative hypothesis. For alternative hypothesis where a beta is larger than some value, then it's actually a right-sided test or a right-tailed test. If beta is lower than some specific value, then it's actually a left-tailed test. Okay, so be careful on the choice of the critical value. It could be positive, it could be negative, depending on the alternative hypothesis that you're testing. Okay, any questions on how you determine the critical value? Go ahead. Okay, just one point, I guess. So as you go from the left, to the right, the significance level actually decreases. Okay, and at the same time, you can see that from you move to the left to the right, as the significance level decreases, the critical value actually increases. Okay, so as you have a lower significance level, then you want to have kind of like a more evidence to support that to reject the null hypothesis. And so this reduces the probability that you reject the true null hypothesis. So you really have to be sure, so that you to reject the null hypothesis. That's why you have larger critical value as the significance level decreases. Okay. Another point that I'd like to make is that if the degrees of freedom is very, very large, then you can observe the critical value is quite close to the critical value under the normal distribution. So for the case of 5% significance level, it's 1.645, which is quite close to the normal or the standard normal distribution. If the alpha is 0.025, it's actually 1.96, which is also the critical value under the standard normal distribution. So that's another remark that I'd like to make. Okay, and so this is just one particular example. I've mentioned to you that the Mincerian equation has an hypothesis that as you work longer or as you gain more years of experience in the labor market, then there is a positive relationship between that years of experience with log wages. And so here there is a positive relationship. And so you can state that the alternative hypothesis to be beta experience larger than 0. Okay, just some technical note. Some people write the null hypothesis as beta experience equals to 0. Some people write it equals or less than 0. It doesn't really matter. For brevity, I use the following null hypothesis. So just beta experience equals to 0. Okay. All right. And so we're going to conduct a one-sided alternative test because one will expect a positive effect of experience on hourly wages or no effect at all. Okay. So again, we're going to use a one-sided alternative because we're going to expect a positive effect of working experience on wages or no effect at all. Okay. So that's the idea. Okay. So it's very straightforward to calculate. So the t statistics, which is the t ratio, is just 0.0041 minus 0 divided the standard error, which is 0.0017. And you can find that the t ratio, the t statistic, is close to 2.41. And you have a large degree of freedom, which in this case is 522. Okay. Now, the next thing that you like to do is that you need to determine the critical value. Okay. So we can determine several critical value depending on the significance level. You have critical value when the significance level is 0.01, which is 1%. You have a critical value when the critical value is 5%. Okay. So what do you say in this instance? Okay. If you are unsure, you can always draw it. And actually, I always recommend students to draw it. So it's going to provide you with kind of like a more natural illustration on the hypothesis testing that you're after. Okay, so this is the 5% significance level that we assume. Okay, and the critical value is 1645. And your estimated coefficient is someone right here, which is 2.41. So in this particular case, your t statistic is larger than the critical value, and so you can reject the null hypothesis at the 5% significant level. Okay. Now, what if you use not 5%, but suppose that you use the 1% level? Okay. So suppose that this is 1%, and then the critical value for 1% is 2.326. And then again, your estimated coefficient is 2.41. So your estimated coefficient, your t statistic for the estimated coefficient is 2.41, which is still larger than the critical value at the 1% significance level. And so what you can conclude is the years of working experience has a positive effect, has a significant and positive effect on hourly wages at the 1% significance level. Okay, so that's how you conclude given the evidence or the data that you have. So that's on one-sided alternative. Okay, so again, the effect of experience on hourly wage is positive and statistically significant at the 1% level. Okay, I just want to reiterate, the effect of experience is positive and is statistically significant at the 1% level. Okay, so if you find that it's significant at the 5% and then at the 1% level, then you want to state that it's significant at the 1% level instead. All right, so that's testing against one-sided alternative. I provide you with an example in Stata on how to actually do a one-sided test. So if we have time, we'll revisit. But if we don't, then I'm going to assume that for your independent learning, and Helga is actually going to go through perhaps a couple of examples using Stata. Okay, but you already have an access to the Stata.do file, so you can start from there. Okay, so I'm going to skip this one as we've discussed the significant level, and I'm going to go through directly to testing against two-sided alternative. One question. Okay, good. All right, so if we have time, let's revisit the exercise in Stata, but now let's go through testing against two-sided alternative. So the idea is that if we have a theory and then the theory says that, there is that positive relationship, or the theory says that there is that negative relationship, we can use that theory to state the hypothesis. Okay, so the hypothesis that beta j is larger than 0, or alternative hypothesis that beta j is lower than 0. Okay. However, if we're unsure that there will be a positive or there will be a negative effect, then it's actually conservative for us to assume that the beta j is not equal to 0. So we don't know whether it's positive, we don't know that it's actually negative. Okay. Okay, so in this particular case, we state that the alternative hypothesis is that beta j not equal to 0. So it could be positive or it could be negative. So the idea is still the same. We're going to reject the null hypothesis in favor of alternative hypothesis if the estimated coefficient is too large. Now, be careful. The critical value is not only on the one side, but it's actually on the two sides of the distribution. Okay. Now, suppose this is the illustration. Okay. Again, not a perfect normal distribution, but hopefully you'll get the point. Maybe I should have a predetermined normal distribution. All right. So this is going to be alpha divided by 2. Okay, and this is going to be alpha divided by 2. Okay, so basically this is going to be the t value or the critical value for alpha divided by 2, and then some degrees of freedom. Okay, and this is going to be negative t alpha divided by 2 for some degrees of freedom. Okay, now we're going to reject the null hypothesis if the t statistic is too large. Too large means that it's actually higher than the critical value on the right, or it's actually lower on the than the critical value on the left. So too large in terms of the kind of like the absolute value. Okay, so that's going to be the idea of two-sided alternatives. Again, why do we want a two-sided alternative versus a one-sided alternative? We want to have a two-sided alternative in cases where we don't know a priori whether or not a variable is or will be positively or negatively correlated. Okay. So these are examples of variables that we're interested in. So we want to look at the determinants of college GPA. So we have the high school GPA, we have the ACT. So ACT is basically kind of like an academic test or a standardized test that you take before college admission. In your particular case, maybe it's the Gajah Mada Scholastic Test or the GMST. So that's kind of like the ACT version in Gajah Mada. Okay, so basically it's going to provide us with an information on your academic capability. And the third variable is actually skipped. So skip is the number of classes that you skip. Okay, and we want to test whether or not there is a relationship between high school GPA and college GPA. There is a relationship between the standardized test ACT and the college GPA, and whether or not there is a relationship between skipping classes and then college GPA. Okay, so let's go, I guess, just briskly one by one. We'll start with the high school GPA. And so in the high school GPA, we get that the T statistic is 4.38 and is actually higher than the critical value at 1%. And so we can say that there is a positive and significant relationship between college and high school GPA at the 1% significant level. Okay, now remember, if we want to do the interpretation, we always have to assume, or perhaps you want to explicitly state, ceteris paribus. Okay? It means that all else constant. Okay, so that's for high school GPA. Now, what about the ACT? Okay, so the T statistic for the ACT is 1.36, which is lower than the critical value at the 10% significant level. Okay, so it's even lower than the critical value at the 10% significant level. Now, since it's lower than the critical value at the 10% significance level, we can say that there is no relationship between college GPA and ACT at the 10% significant level. In other words, the effect of ACT on college GPA, or the relationship between college GPA, is 0, or statistically equal to 0, or just 0. Okay. So you're asking, wait, the estimated value is not 0. However, given the standard error, we cannot distinguish 0.015 from 0. Okay. And so estimated coefficient is not enough. We need to know kind of like the magnitude of the distribution. Okay. So if it's actually not precisely estimated, then we'll have to say that it's not statistically different from 0. Okay. The third variable is the skip. We want to know whether negative 0.083 is statistically significant. In other words, we want to know whether the negative 0.0833, is different to 0. How do we do that? Well, we just have to compare it with the critical value. Indeed, it's larger than the critical value in absolute term. So we can also state that the skip is statistically and negatively correlated. It's significant and it's negatively correlated with college GPA. Okay, so the more classes you skip, the lower the college GPA. Okay, so don't skip classes. I guess that's the message of this regression findings. Okay. All right. All right. So I've been saying statistically significant. What do we mean by statistically significant? So basically, if a regression coefficient is different from 0, again, the number could be 0.086, the number could be 2.24. But even if the number is 2.24, but if the standard error is very large, then we cannot actually distinguish 2 from 0. It could be that the number is 2, but it's not statistically significant. But it could be a number that is 0.039, but it's statistically significant. In other words, 0.039 is actually different from 0. Okay. How can we conclude that 0.039 is different from 0, but we conclude that 2.24 is actually not different to 0? Because of the standard errors. Okay. And if you remember, the standard errors is going to depend on the errors of the residuals. It's also going to depend on the sample size, okay, and also on the relationship with the variable with the other variables in the regression. Okay. All right. So this is just a recall on the estimation of the standard error. Okay. So basically, if the number of degrees of freedom is large enough, okay, we can do what's called the normal approximation. Okay. So if it's a two-sided test and you have a significant level of 5%, then the critical value is just 2 or minus 2. That's how you usually use it. It's actually 1.96 to be precise, but I always use the 2 and -2. Okay, so if it's larger than 2 or it's actually lower than -2, then it's statistically significant at the 5% level. That's how I usually use it. Okay, if you want to go, and use the 1% level, then the rule of thumb is larger than 2.6 or lower than -2.6. Again, this is for a case where we have two-sided tests, okay? Because for two-sided tests, we have alpha divided by 2. Okay, so this is the example, for the, this is the example from the Wage1 data. Again, this is something that you'll see in the Stata2 file. So the estimated coefficient for the education is actually 0.644, and then the t-statistics is 11.97. And so given this finding, we can say that, and given the rule of thumb of 2, we can actually state that the education, it has a positive and significant relationship with wages at the 5% significance level. And even further, it's actually significant at the 1% significant level. Okay. So that's the idea of two-sided hypothesis testing. Okay. This is just another example. If you use the rule of thumb, say for alpha of 5%, then the rule of thumb for the critical value is ±2. Okay. And then for alpha equals to 1%, then the critical value, again, for two-sided test is ±2.6. Okay, so in this particular case, we can conclude that the education has a positive relationship and a significant relationship with wages at the not only 5, but also 1%. Again, if you conclude that is significant at the 1% level, then it automatically is significant at the 10 or at the 5% level. Okay. All right, just one more remark that I want to make before I go and then discuss the other point. So if a variable is statistically significant, you can discuss the magnitude of the coefficient to get an idea of whether or not it's economic or practically important. Okay, so you have to distinguish between a statistically significant variable and then an economically significant variable. Okay, it could be that a variable is statistically significant, but perhaps it doesn't really have a meaning on economically or practically. Okay, so if a variable is statistically and economically important, okay, however, it has the wrong sign. Okay, so suppose that we assume or we predict that the estimated coefficient is positive, but we find that it's actually negative. Well, it could be a sign that the regression model is misspecified. It could also be an indication that you might have left out or leave out an omitted or a variable, in which case you have an omitted variable bias. Okay. All right. So that's some of the issues. Okay. Now, another point that I like to make, and it's actually going to be correlated with the discussion that we have in the subsequent slides. So if a variable is statistically insignificant at the usual level, 10%, 5%, 1%, should we drop the variables from the regression? Well, the answer is it depends. Okay, so if you drop the variable, then the problem is that you could be facing with an omitted variable bias. Okay. However, if you include an irrelevant variable, as you recall from the previous chapter, then your regression coefficient will be inefficient. in the sense that your variance will be higher if you include irrelevant variables. So you always have that trade-off. So make sure that if you want to include an explanatory variable in your regression, one, you should base it off on the theory, and then you should also base it off on the previous literature. Okay, and even after you base it off, you base it off on the theory and the literature, and you still get statistically insignificant variable, then you shouldn't drop it. Okay, if you drop it, then you may be facing an issue of omitted variable bias. So that's going to be the key. Okay. Any question before I move to the next phase of discussion?
Sir, can I ask?
Yes.
So in the previous example, it is stated that different variable we use different significant levels. So how we determine each variables to use a certain significant level. So for example, the GPA use the 1% significant level, the ACT use 10% significant level, and the skip one we use the 1% significance level. So how we determine for each variable to use a certain significant levels. Thank you, sir.
Okay, so you don't basically change the significance level across variables, but what you need to do first is to set the significant level that you like to do comparison of. So, for example, okay, I'm going to use a set of significant levels, which are 1%, 5%, 10%. Okay. Now, the idea is that if a particular variable is already significant at the 1% level, as in the case of the high school GPA, then it automatically is significant at the 5% level as well as at the 10% level. Okay. However, for the case of ACT, it's not significant at the 10% level. Okay. So it wouldn't be significant at the 5 and the 1% level. Okay. And the case of skip will be similar to the case of high school GPA. And so we don't choose significance level arbitrarily, but we actually set the significant levels that we want as a reference, which is 1, 5, and 10%. And so we have to evaluate one by one. If one is not statistically significant at the 1% level, we'll then evaluate at the 5% level. If it's significant at the 5% level, stop there. Okay, but if it's still not significant at the 5% level, we're going to evaluate whether or not it's significant at the 10% level. Okay, if it's not significant at the 10% level, then we can conclude that it's actually not statistically significant. We don't want to push beyond 10%. Why? If we push beyond 10%, then there is that higher likelihood of rejecting the true null hypothesis. Okay. All right, good. One more question before I go into the next discussion. Okay, very good. So far we've been testing the null hypothesis that beta j is actually equal to a particular value, which is 0. However, in some cases, we want to test the value of beta j not equal to 0. So for example, it could be a particular constant. It could be equal to 1, it could be equal to 2, and so on and so forth. Okay, so suppose that you're interested in a particular elasticity, and the theory says that the elasticity is equal to 1. So in that case, you want to test whether or not beta j is equal to 1. Or you want to test whether the elasticity is actually -1. And so your beta j, the null hypothesis, is that your beta j is equal to -1. So in this particular case, we can assume beta j is equal to some constant aj. It could be positive, it could be negative. It doesn't have to be 0. Okay. So the t statistic is going to be a bit different. Instead of just subtracting it, with 0, we're going to subtract it with the assumed value or the assumed value of the parameter in the null hypothesis. And so since the assumed value of beta j in the population is aj, then we're going to subtract aj from beta hat j. Okay, so there is no difference in the standard error. Okay, since the standard error is the standard error that we get from the estimation. Okay, so this is an interesting hypothesis that we like to test, which is campus crime and enrollment. So one interesting hypothesis that we like to know is whether or not crime increases by 1% if enrollment increases by 1%. So this is what's called the one-to-one relationship. So if enrollment increases by 1%, then whether or not crime will increase by 1% as well. Okay, so now again, what we'd like to test is that whether or not it's a one-to-one relationship. Okay, and the alternative hypothesis is that beta crime is not equal to 1. So not equal to 1 means that it could be larger than 1, it could be lower than 1. Okay, so we do an estimation again with the data that you have from the Wooldridge data set and the do file. You can replicate this number and then you get 1.27. Okay, 1.27, is it 1? And if it's 1, then we do not reject the null hypothesis, or it's actually far away from 1. If it's far away from 1, we reject the null hypothesis. Okay, and so how do we do that? Well, we just have to do the t statistic. So the t statistic is now 1.27 minus 1 divided by 0.11. Okay, and we're going to get a t statistic which is close to 2.45. Okay, now recall that the rule of thumb for alpha equals to 1% is 2.56. Okay, so 2.45 is actually lower than 2.56, and so it's not statistically significant at the 1% level. However, it's still larger. Oops, oh, I don't know where this comes from. Okay, so however, it's actually still larger than the rule of thumb of 2, which is at the 5% significant level. And so we can reject, the hypothesis at the 5% level. And so what do you conclude? You conclude that there is actually more than, the elasticity of crime and enrollment is actually higher than 1. If enrollment increases by 1%, then crime actually increases by more than 1% and is statistically significant at the 5% level. So that's the idea of testing. Any question from this? So your question, probably the natural question, will be, where do you get this one-to-one relationship? Usually it's from the literature. So the literature would like to test the hypothesis that there is a one-to-one relationship. Okay. Literature also means the theory.
Sir, may I ask?
Yes, go ahead.
For the number of 0.11, is it usually provided? I mean, the standard error, is it usually provided by the question, or sometimes do we need to calculate it manually, sir?
No, yeah, I don't think you should calculate it manually. It's usually provided. It's going to be too cumbersome for you to calculate it manually. And again, the idea of learning at the 21st century is not about calculating, but it's more on the conceptual and the critical thinking behind it. Okay, I'll let the software do the magic, basically.
Okay, thank you, sir.
Okay, sure. All right, so I'll continue. Maybe in the previous slide, you've seen p-value. And so what's the meaning behind this p-value? So p-value is actually a very important and very valuable information that you like to get from your regression. So p-value is basically the smallest significance level at which the null hypothesis is still rejected. Okay, so two keywords. the smallest significance level at which the null hypothesis is still rejected. Okay, it's called the p-value. Okay, so if you have a small p-value, okay, so suppose that your p-value is, say, 0.005, which is quite small, it's actually the evidence against the null hypothesis. Okay, so if you have a p-value of 0.005, it means that it's the smallest significance level at which the null hypothesis is still rejected. Okay, since it's very low, then it means that you reject the null hypothesis. Okay, however, if you have a p-value that is relatively large, say 0.152, okay, so this is the smallest significance level at which you reject the null hypothesis. Okay, but it's very large. It means that you're going to be prone to the type 1 error. Okay, and so basically what you're going to do is you're going to compare the p-value and the significance level. Okay, so suppose that your p-value is lower than your significant level. Okay, suppose your significant level is 1% or 0.01. Okay, so if your p-value is lower than 0.01, it means that you reject the null hypothesis at the 1% significant level. Okay, however, if your p-value is between 0.01 and say 0.05, it means that you reject the null hypothesis at the 5% level. Okay, but you cannot reject the null hypothesis at the 1% level. Okay, so p-values are going to be more informative than the t-test, the t-ratio at fixed significance level. Okay, and so basically what I do is that I usually look at the p-value and then compare that to the significance level of interest. It could be 1%, it could be 5%, it could be 10%. Okay, and so I guess using the p-value is going to be more informative than just using the t-test. Why? Because by doing the t-test, you need to find the critical value, and then you need to compare the t-test with the critical value to make a conclusion about the hypothesis. Okay, but if you have the p-value, then you just have to compare it with the assumed significance level. It could be at the 1% level, it could be at the 5% level, it could be at the 10% level. Okay, any questions on the p-value before I go and discuss confidence interval? Okay. All right, so let's discuss confidence interval. Again, this is, I think, an important kind of like an important idea on estimation. So far we've talked about point estimate, and so a confidence interval will provide you with an idea on how a particular estimate could vary, okay, given a significant level. Okay, so the first thing that we'd like to do is we'd like to set the significance level. It could be the 1%, it could be the 5%, it could be the 10%. So suppose that we choose alpha equal to 5%, okay? So the significance level at the 5%. And so we're going to have 100 minus alpha, alpha is 5 in this case. And so 100 minus 5 is 95% confidence interval. So 95% confidence interval is constructed by the estimate beta j plus minus the margin of error. Okay, so how big is the margin of error? The size of the margin of error is actually the critical value multiplied by the standard error. Okay, so basically this is the critical value multiplied by the standard error of the estimate. Okay, so what's the interpretation of the confidence interval? Okay, so basically the bounds of the interval are going to be random. Okay, so it's really going to depend on the sample. Okay, since if you have a different sample, then the interval is going to be different. So that's one. The second is that in repeated sample, the interval that is constructed in the above way will cover the population regression coefficient in 95% of the cases. I'll give you an illustration. Okay, so suppose that this is the true value. Okay, so this is the true. Oops, oh, what did I do? Okay, so suppose that this is the true value. Okay, so this is the true value. So in a particular sample, your interval includes the true value. Okay, in another sample, you construct an interval and the interval is random and you include the true value. In another sample, you also include the true value. In another sample, you also include the true value. But in another sample, you do not include, the interval does not include the true value. Okay, so the idea is that if you have 100 interval, 95% or 95 out of the 100 intervals will include the true value of the parameter. So that's the idea of 95% confidence interval. So if you have a 99% confidence interval, is that 99 out of 100 intervals that you get from repeated sampling is going to contain the true value. And so, you know, if you have a wider, like a 99% confidence interval, it means that you're more confident with the estimate that you get. In other sense, if you have a 99% confidence interval, you're more confident that the true parameter is within, the intervals. So again, setting up the confidence interval is quite straightforward. So 1 minus alpha is going to be the confidence level. It could be 99%, it could be 95%, it could be 90%, depending on the value of alpha. Okay, so we can construct the confidence interval because we exploit the fact that the estimation, the beta hat, is normally distributed estimate with a normal distribution. So basically, if we don't have the if we don't have the distribution, if we don't have the population value for the variance, we use the sampling variance, and so we have the sample variance, and so we're going to assume a distribution, which is basically normal, by the way. Okay, so here we only consider two-sided confidence interval, and by default, the confidence level is 0.95. In other words, we're using just alpha of 0.05. We don't really use, we rarely use alpha of 1% or alpha of 10%. Okay, but you can do it. Not saying that you cannot do it, but in default, we use a 95% confidence interval. In Stata, for example, they also will report you the 95 confidence interval by default. Okay, so these are just several confidence interval or based on the value of alpha, and so alpha is going to determine the critical value. For a very large sample, the critical value for 1% significant level is about 2.6, and for 5% level is about 2, and then for 10% level is about 1.65. Okay, now the question is, given the same estimates, given the same standard error, and given the same sample size, which confidence interval is going to be larger, or which confidence interval is going to be wider? Is it the 99%, the 95%, or the 90%? Which one? which one is going to be larger? All else the same. So estimate is the same, beta hat J the same, sample size is the same. The only difference is the significance level and thus the confidence interval. Which one is going to be larger? The 99, the 95, or the 90% confidence interval?
The 99, sir.
99, sir.
Yes, exactly. Very good. So it's going to be the 99 confidence interval. Why? Because we have basically a larger critical value. Okay. And so it means that, the wider the confidence interval, the more confident that the true value of beta is within that interval. And so 99% confidence interval includes more, have more likelihood, has a higher likelihood to include the true parameter. Okay. All right. So at the end of the day, we've been discussing inference and what does confidence interval have to do with inference. Okay. So I also like to use confidence interval to do hypothesis testing. Okay. So basically, if alpha j is not in the interval, it means that you reject the null hypothesis in favor of the alternative hypothesis. Okay. So suppose that your null hypothesis is beta equal to 0. If 0 is not in the confidence interval, it means that you reject the null hypothesis. Okay. Again, if you test a hypothesis that beta j is equal to 0, and then 0 is not in the interval, it means that you reject the null hypothesis. Okay. So that's the idea of using the confidence interval for hypothesis testing. Okay. So I'll provide you guys with a brief example. So we have a model of firms' R&D expenditures. And so in this particular case, we regress the log of research and the expenditure on the left-hand side, and then log sales. Okay. And on the right-hand side, we also have the profit margin. So we have all the information available to determine the confidence interval. And so let's start with the annual sales. So what is the estimated confidence interval for the annual sales? So basically, it's the estimated beta hat j plus minus the confidence interval, the critical value at the 5% level, multiplied by the standard error. And the standard error is just 0.060. Okay. And so the estimated confidence interval is between 0.961 and 1.21. The question is 0 included in the interval? Yes or no? So is 0. So again, we want to test that the beta sales is equal to 0, and then beta sales is not equal to 0. Now the question is whether 0 is included in the interval, yes or no?
No, sir.
No, sir.
So 0 is actually outside of the interval. And since 0 is outside of the interval, then what can we conclude? We can conclude that sales has a positive relationship and a statistically significant relationship. Okay. And so if 0 is not included in the interval, okay, it means that log sales is a statistically significant variable. Okay. Now let's look at the confidence interval for the profit margins. Okay, so basically profit as percentage of sales. So after we do some calculation, we're going to get that the confidence interval is between negative 0.0045 and 0.0479. Okay, so does 0 being included in the interval? Yes or no?
Yes, sir.
Yeah, so it's 0 is within the interval. And so since 0 is within the interval, then we cannot reject the null hypothesis. And if we cannot reject the null hypothesis, then we're going to conclude that there is no effect of profit margin on the log of R&D expenditures. Okay, so that's how you would use a confidence interval on hypothesis testing. Okay, so far you've used t-statistics and critical value, you use p-value, and you use confidence interval, and so you see that variation on how you use that basically over time, over different. That's a different ways on using the statistics that you get from the estimation for hypothesis testing. Okay, so many information that you can get from. Okay, questions on testing on confidence interval. Okay, all right, good. So I guess this is going to be the last part of our lecture today, but I think this is kind of like the more important one. So please pay attention. I understand that this is the last miles and the last minute. Everyone's fatigued, but bear with me for several more minutes. And this is going to be quite important for us to understand inference in total. So in the previous discussions, we only focused on whether or not a particular variable is statistically significant or not. Okay, so we haven't gone through situations where whether or not a group of variable or a set of variables is statistically significant or not. And so what we're going to discuss now is testing multiple linear restrictions. Okay, so the F-test allows one to test multiple hypotheses about individual parameters simultaneously. Okay, so this is a case of baseball player salary, which is quite large. And there are several variables which determine the salary of a baseball player. So the first one is the number of years he played in the Major League Baseball, and then the number of games per year. They can play like hundreds of games every season. So basically they play every day for several days and then take a break and then play again for several days. And in one particular game, it could get quite long. One particular baseball game could get into 5 hours. And so basically, usually you bring a book or do your homework and watch a baseball game. Pretty cheap in some cities as well, so you can enjoy it. And then it's actually the batting average. So batting average is the amount of ball that you hit every time you bat. And then you guys have heard of the term home run, basically. So this is the number of home runs that a particular player hit in a year. And then this is called the RBI. RBI is basically runs batted in. And so if you hit a ball and then your teammate passes the home plate, then it counts as a run batted in. So if you hit a ball and then 2 of your teammates actually pass the home plate, then you have 2 runs batted in. And so basically the variables batting average, home runs per year, and runs batted in is actually a performance variable. And then the performance variable is going to determine whether or not your salary is high or low. Okay. So for example, in soccer or in football, then the number of goals, the number of games that you play, and then the number of assists, and then the ratings could be a determinant of your salary. Okay. So that's also important performance variable. Okay, So what you like to do is you want to test whether or not these variables at the same time or simultaneously affect salary. Okay. And so what you're going to test is whether or not beta 3 equals to 0, beta 4 equals to 0, beta 5 equals to 0 simultaneously. Okay. And then the null hypothesis is that the H null is not true. Okay. So you do an estimation first of the what's called unrestricted model. So the unrestricted model is a regression with all the variables. That's why it's called the unrestricted variable. Okay. So after you get an unrestricted variable, you can see that the batting average, the home runs per year, and then the runs batted in per year is not statistically significant. Okay. Again, the performance measure individually are not statistically significant. How can you say that it's not statistically significant just by looking at the coefficient and the standard error? Okay. So here you can see that the estimated coefficient is smaller than the standard error. Okay. If your estimated coefficient is lower than your standard error, then your t-test is going to be lower than 1. If your t-test or your t-ratio is lower than 1, then you do not reject the null hypothesis. If you do not reject the null hypothesis, then it's not statistically significant. Then a question arises, well, if performance measure is a significant determinant of salary, then why is it not statistically significant? Okay, that's going to be the question. Perhaps individually it's not statistically significant, however, altogether or simultaneously they're statistically significant. So that's where we're after. Okay, so individually probably is not significant. However, taken together, the three variables could be a statistically significant determinant of salary. Okay, so that's what we're going to discuss. And so to be able to test that, we're going to do what's called the estimation of the restricted model. So the estimation of the restricted model is an estimation without the three variables. Okay, and so you're going to get what's called the sum square residual. Okay, what's a sum square residual? Sum square residual is basically the variation of the variable of interest that cannot be explained by the model. If you leave out the three performance variable, will you get a larger or a lower sum square residual? Basically, if you leave out some variables, your sum square residuals will be higher. Okay, so the higher the variation that cannot be explained by the model. Okay, so what we're interested in is whether or not by dropping the variables, the sum square residual will increase and whether it's actually going to increase significantly. And so we're going to test that using the F statistic. Okay, so basically it's going to be the sum square residual of the restricted model, which is the model above, and then the sum square residual of the unrestricted model, which is the model previously, and Q is the number of restriction. Okay, and divided by the sum square residual of the unrestricted divided by the degrees of freedom for the denominator, which is n minus k minus 1. Okay, so this test is going to follow an F test with degrees of freedom q at the numerator and then degrees of freedom n minus k minus 1 at the denominator. Okay, all right, so this is going to be the distribution of the F test. It's going to take only positive values. Okay, so this corresponds to the fact that the sum square residuals can only increase by moving from the alternative hypothesis to the null hypothesis. Okay. So this is the illustration on the F distribution. So the area is just 5%. It's a one-sided test. Okay. And so if you have an F statistics that is higher than the critical value, then you're going to reject the null hypothesis. Okay. You can also use the p-value. Okay, it's valid to use the p-value. If the p-value is lower than the significant level, then you can reject the null hypothesis. Okay, all right. So this is like the F table, but I rarely use the F table. I use the p-value statistics a lot. Why? Again, it's more informative for a fixed significant level. But you know, if you look at the denominator and stuff like that, it's going to be quite cumbersome because you have to look at the table, and a lot of times your denominator degrees of freedom is on hundreds because you have a lot of observations. Okay, so it's quite difficult that way. So I'm gonna kind of like skip a bit on this and then just discuss the p-value. Okay, so basically we're going to test you know, the decisions. So the key here is that the number of restrictions is 3. So beta 3 equal to 0, that's one restriction. Beta 4 equals to 0, that's one restriction. Beta 5 equals to 0, that's another restriction. So in total, we have 3 restrictions, okay? And so we're going to get a critical value of 3.78, and our F test or F statistics is 9.55. Okay, what does it mean? It means that you reject the null hypothesis. Okay, so another way of looking at it is by looking at the p-value. So the p-value is 0.0000. It means that it's lower than alpha of, say, 1%. If it's lower than the alpha of 1%, what does it say? It says that it's significant at the 1% level. In other words, we reject the null hypothesis at the 1% level. Okay? So in this particular case, what do we mean by we reject the null hypothesis? So in the case of multiple linear restriction, and we reject the null hypothesis, it means that the variables are jointly significant. Okay, so remember that home runs per year, batting average, and then runs batted in per year is not statistically significant individually, but however, jointly they are significant. So what could be the reason that, you know, individually they're not significant, but jointly they're significant? So the likely reason is that there could be multicollinearity between them. So there is a linear relationship between batting average and runs batted in, for example. The more you hit during your bat, the more likely that you're going to have your teammates batted in. And so given that degrees of multicollinearity, what happens? Remember, the formula for the standard error of beta hat j is going to be the ratio between the variance of the residual and then the sum square of the variable, and then 1 minus r squared j. Okay, so the issue is that the r squared j will be relatively high, and so if the r squared j is relatively high, then the standard error will be high. And if the standard error is high, what happens to the t-statistic? The t-statistic tends to be lower. If the t-statistic tends to be lower, then you tend to not reject the null hypothesis. So that's the issue if we have multicollinearity among variables of interest. Okay, I'm going to stop here for a second. I'm going to take one question before I move to the next discussion.
Sir, just a clarification.
Go ahead.
So given that we want to test these explanatory variables simultaneously, does that mean that the f-test is never used for simple linear regression models with only one explanatory variable?
You can actually still use it. So this is actually a fun fact. If you just test one variable, okay, your t-square, so the t to the power of 2, the t-statistic square is actually equals to the f, okay, if you just test one variable, okay. So in general, the answer is yes. If you just test one variable, then you can just use t-statistics. You don't have to use the f-statistics. But just a fun fact that if you have one variable, t-square is actually equal to f. Okay, good. I'm going to continue to the next discussion. So far we've supposed that we have 5 variables and we want to test whether or not 3 variables are jointly significant. Okay. In other cases, we also want to know whether or not there is an overall significance of a regression. Okay. So basically, we want to know whether or not x1, x2, x3, x4, and so on until xk are jointly significant. In that case, the null hypothesis is that beta 1 is equal to beta 2 and so on, beta k equals to 0. And the alternative hypothesis is that the null is not true. Okay, so basically you have the restricted model. The restricted model is when beta 0, beta 1, beta 2, and so on is equal to 0. So this is basically just the average of y. Okay, so if you regress y on a constant, then beta 0 is just going to provide you with an average of y. Okay, so basically the restricted model is going to have an r square of 0 by, because all the variation of the model will be discussed by a variation in the error terms, okay, or the residuals. Why? Because this is a constant. Okay, so all variation of y cannot be explained by a constant, so it's all going to be explained by the residual. Okay, and so in this particular case, since the SSR restricted is going to be 1, okay, and then the SSR unrestricted is going to be some value, then we're just going to use the r square of the unrestricted. Okay, and what's the number of restriction? The number of restriction is actually the number of variables. Okay, now Stata is going to automatically report this statistic in the regression. So when you do your exercise using Stata, you're going to it's going to be reported directly into the regression function. So it's going to be quite straightforward. Okay, any questions? I'll take one before I go and discuss another interesting example. All right, so for of you guys who are interested in looking at urban economics, housing economics, and in particular, you guys are interested in looking at the hedonic pricing model. It's actually a very interesting topics that we develop here in the Department of Economics. It's interesting in the sense that the property in Indonesia is rising quite fast, and the data is actually more and more readily available. So for example, if you go to rumah.com or you go to rumah123.com, you'll see like many properties, and then from there they're going to provide you information on the prices and so on and so forth. Okay, so you can do like a web scraping and then to get the data, and then from that web scraping data you can do a regression to see whether or not there is a relationship between the number of bedrooms, the size of the land, the size of the building, and stuff like that. However, what's interesting is to see whether or not the price assessment are actually rational. Okay, so if the price assessment is rational, it means that, excuse me, a 1% change in the assessment should be associated with 1% changes in price, okay? And so if the assessment is rational, it means that other known factors should not influence the price conditional on the assessed value, okay? So again, if the assessment value is rational, then other factors should not influence the price, again, conditional on the assessment value. And so what we're interested in is that whether or not the value of beta 1 is actually equal to 1, and then beta 2 is equal to 0, beta 3 equals to 0, and beta 4 equals to 0. So that's what we're interested in, okay? And so how do we do that? Well, the same thing. You have the unrestricted model, which is this, and then you have the restricted model. What's the restricted model? Well, it's log price, beta 0, log access, and then 0, 0, 0, and then unobservable. That's the restricted model, okay? So you have the unrestricted model, you have the restricted model, and then from the test statistic, you'll get the F test. So the F test is 0.661, which is quite low. And this is a evidence that we do not reject the null hypothesis. So if we do not reject the null hypothesis, then we can conclude that indeed the housing assessment or the price assessment is actually quite rational, okay? Now, again, you're going to go through this in your Stata2 file. And so make sure that you go over and look at the Stata2 file and then do the exercises and confirm what has been discussed in this particular meeting, okay? So lastly, I just want to point out that the F-test only works for linear hypothesis, okay? So this one, beta 1 equals to beta 2 equals to 0. How many restrictions do we have? In this case, we have two restrictions. We have beta 1 equal to 0. We have beta 2 equals to 0. Okay, so we have two restrictions. In this case, can we do this? Is it a linear restriction? The answer is yes, it's a linear restriction. How many restrictions?
1, 2.
Exactly. Very good, David. So we just have one, which is beta 1 equals to beta 2. Okay. What about this one? Can we do this? Is it a linear restriction? So yes, it's a linear restriction. Basically, it's beta 1 equals to 1 minus beta 2, and then we have beta 3 equals to 0. Okay. So we have how many restrictions? So this is one particular restriction. This is another particular restriction. So we have in total two restrictions. Okay. How about the last case? Is this a linear restriction? The answer is no, it's not a linear restriction. Why? Because it's beta 1 multiplied by beta 2. So it's not a, basically it's not a linear restriction. Okay. All right. So I guess that's kind of like the lecture for inference, which is quite long and quite comprehensive. I think it's going to provide you with the foundation that you need to do the regression and then determine whether or not a particular variable is significant or not. I just want to provide you with an overview of the do file. If you haven't had a chance to look at the do file, please look at the do file. And then you're going to go through several examples of one-sided tests and then two-sided tests with the same data that was given in the slide deck. Okay, so be sure to look at that. And then if you have any questions, you can ask it during the tutorial, or you can also ask it in the next session. All right. So I'm going to stop here so that you can take a break before your next lecture if you have one. If you haven't, then you can do other things like studying. All right, I'll stop here. Have a good day, and I'll see you in the next course. Bye-bye.